A very warm welcome back to the session. We trust you had a wonderful insight into the panel discussion. We now head to the final session of the day, which is Sustainable Refrigeration Systems in Retail Stores. For everybody who is joining us, I'm your MC, Nisha Nair. I serve as the Associate Director at VK Powermaster. And our next session for the day is by Mr. Michael Schaffer. Mr. Mike serves as the Senior Director of Technology at Hussmann. He has close to 35 years of experience in engineering, operation, and manufacturing verticals. He has also served on international assignments in Mexico and Brazil. He has a bachelor's degree in mechanical engineering from the University of Missouri in Rolla. He also holds an MBA from the University of Missouri, St. Louis. So a very warm welcome to Mr. Mike, and I now request you to please take over the session.
All right. Thank you very much for inviting me to this this event. I appreciate the invite from REFCOLD. So today I'll be talking about sustainable refrigeration systems for retail stores. I work for Hussmann. I'm the Director of Technology, and I've been in the industry for 35 years now. So anyway, thanks again, and we'll go ahead and get started. The learning objectives. We'll talk about some of the current strategies for retail systems, talk about assessing global warming impact in retail stores, and then we'll have an overview of the current sustainable refrigeration systems. So for the agenda for today, we'll talk a little bit about the regulatory forces that are driving and shaping the industries. In response to those forces, we'll look at the different strategies that can be employed in the retail store. And then we'll look at assessing supermarket carbon emissions. So the different types of refrigeration systems that we'll look at CO2 Transcritical, CO2 Cascade Hybrid Systems. We'll look at a number of distributed systems, including macro and micro, and then we'll have a little bit on self-contained. After that, I'll follow up with a summary. So what are the regulatory forces? I think everybody's pretty familiar with the Kigali Amendment to the Montreal Protocol and the drive to push the production and consumption of high GWP refrigerants or hydrofluorocarbons down to 80%. Here in the United States, there's a number of legislation activities. One is related to the different states, whether it's California or United States Climate Alliance. In the absence of a federally mandated regulation of the refrigerants, the states have been very active, especially the progressive states. Recently, the U.S. Senate passed the American Innovation Manufacturing Act, which sets the same HFC reduction targets as Kigali and gives authority to the EPA. So these regulatory actions are driving changes in our industry, changes into the refrigeration system designs, and we'll get into some of that. So what are the strategies? We have 4 focus areas when we talk about reducing carbon footprint in commercial refrigeration stores. The first one will be lowering the GWP of the refrigerant, lowering the amount of refrigerant in the stores, and then we'd like to lower the leak rates for refrigerants. And then the other piece that comes into play is reducing energy consumption. And that comes about relative to choosing the most energy efficient system, as well as store design from a merchandising perspective. We've seen a tremendous change in our industry where open cases, whether it's dairy or deli, predominantly have doors on the cases. So that reduces the overall energy requirement by 50 to 60%. So the 3 strategies we'll focus in on predominantly would be the lower GWP, selection of the refrigeration architecture to utilize a low GWP refrigerant, certainly looking at natural refrigerants as a very good choice. And then in terms of lowering the charge in the stores, some of the system architectures are suitable for lowering the charge, And that would include the distributed, microdistributed systems. And all those lead to less piping in the store, which ultimately would lead to lower leaks. And then, there obviously has to be a big focus on lowering the leak rate. That includes, best practices. That includes, trying to manufacture hermetically sealed units. So how do we assess the supermarket refrigeration carbon emission? So we look at, one of the metrics is that we look at is the total equivalent warming impact, which is a function of the direct emissions and the indirect emissions. So direct emissions are simply the leaks of the refrigerant from the equipment. And that would simply be the GWP of the refrigerant times the leak rate times the charge. So as an example, leaking 1 kilogram of 404A is equivalent to leaking 3,900 kilograms of CO2. On the indirect side, this is a measure of the amount of CO2 emitted due to the fossil fuels that are burned to generate electricity. So that will vary by country. And for this example, looking at the illustration, the effect of reducing the GWP can be visualized comparing 404A, 407A, and 448A. This would be a centralized DX system with identical leak rates and charge sizes. So you can see the contribution of both the direct and indirect emissions. So when we look at the direct emissions, we're looking at the leaks of the equipment. So we want to be cognizant of the charge size and the GWP. So, certainly smaller systems will reduce the overall charge, and then the smaller systems by definition would have shorter piping and a lower leak rate. And then obviously we want to choose the lowest GWP refrigerant as possible, and some architectures are once again more suited for that. In this example, R290, given the charge size, is going to have a much smaller refrigerant charge leak rate. And this illustration on the right would be the effects of reducing the charge size in GWP, comparing the centralized parallel rack compared to the distributed system and a microdistributed system. So clearly the microdistributed with a natural refrigerant only has the indirect contribution, excuse me. And then CO2 would be very similar to what was shown here in green for the microdistributed. So what are the refrigeration systems? We're going to go ahead and look at these systems, as I mentioned before, in the agenda. We'll start with CO2 Transcritical. So from a strategy perspective, this is clearly lowering the GWP. The system is characterized by 2 stages of compression. This would be a simple booster system, which by definition, the transcritical system is going to operate above the critical point of the refrigerant for some period of time during the year. So this system has 2 stages. If the store would have low temp cases, the low temp would discharge into the suction of the high stage. Once again, the system would employ a gas cooler that would either be air cooled or adiabatic, as opposed to a conventional condenser. During the subcritical performance, it would act as a condenser, but transcritically, it's a gas cooler. The system also has a high pressure regulating valve, which is going to try to regulate the outlet temperature and pressure based on the ambient conditions to try to maintain the highest refrigeration effect and efficiency. During the subcritical operation, it will be designed and controlled to maintain a certain amount of subcooling. And then, of course, this has an intermediate pressure receiver or a flash tank, Yeah, also of note, the system would have electronic expansion valves. So what are the considerations? In general, CO2 transcritical systems are going to be more complex than the standard DX systems, and therefore require higher technical skill for installation as well as maintenance. And generally speaking, there's a higher first cost as compared to DX, although component costs have been coming down over the last few years. A lot of activity in Europe in terms of developing systems. As I mentioned before, it requires more controls or EEVs. High-side equipment also has a lot of controls. Another consideration would be system faults. So if you had a system fault, because they're connected, you're likely to affect the entire refrigeration system of the store. So CO2 operates at high operating pressures, and therefore, in the event of a power outage, it has a higher standstill pressure. So there may be requirements to do some auxiliary cooling in the event of a power outage. The other thing to note, of course, that we talked a bit about is that it's lower efficiency in the CO2 transcritical has a lower efficiency in the warmer climates because it's operating predominantly in a transcritical mode. The other consideration is the amount of water that's required for the system if you're using an adiabatic gas cooler. And then there's been a lot of gains over the standard booster system, by parallel compression, ejectors, and subcooling. So the simple example related to the TWE calculation for deli. On this example, we used a small store load, roughly 17.6 kilowatts for the low temp and almost 53 kilowatts for the medium temp, and assuming a 15% leak rate. Looking at the average distribution, temperature distribution for deli, you can see that there's a number of months that the system would be operating transcritically. And then looking at the power consumption, annual power consumption for both the low temp and medium temp, you can compare the three different types of systems. In this example, looking at 404A on the low temp, 134A on the medium temp for the centralized DX system, and that would have the lowest power. The booster system comes in the close second, and the cascade CO2 system would have the most annual power. So looking at the advantages of transcritical, and using natural refrigerant CO2, obviously this would be that it's future-proof in terms of refrigerant regulations. The system operates very efficiently at subcritical, and as I mentioned, there's a number of strategies to improve upon the standard booster system, such as ejectors and parallel compression. CO2 has very good heat transfer properties in terms of volumetric efficiency, as well as latent heat of vaporization, and that results into smaller tubing sizes. So therefore, the installation costs will also be directly related to that in terms of the refrigerant piping. And the compressors have smaller displacement, but not necessarily smaller motors because of the high compression ratios. So we look at the CO2 emissions for that simple example of deli. The DX case obviously is very pronounced due to the direct and indirect leakage, and then also calculation, and then also in terms of the booster looks the best because there's only the indirect effect. And then the cascade has a slight direct effect due to the 134A leaking at a 15% rate. So the next system we'll look at is a cascade CO2 hybrid system, another lower GWP architecture or strategy being employed. In this particular case, there's essentially two racks, the lower cascade and the upper cascade. The low temp would be in the lower cascade, and that would be operating subcritical CO2. Would have EEVs on the systems, and then that would be rejecting that heat through a cascade heat exchanger, and that load would be carried by the medium temp system. So the medium temp system would be more than likely an HFC rack, would have an air-cooled condenser, and the other aspect of it is that the medium temp would be designed for the full load, including obviously the low temp heat rejection. So looking at the considerations, we've already talked a little bit about the power consumption. As CO2 transcritical, these are closely coupled systems, so a fault on the medium temp side can affect obviously performance, the uptime on the low temp. Medium temp is sized for the full store load, as I mentioned, and then given the high standstill pressures on the low temp, you may still require some auxiliary cooling in the event of a power outage. So the advantages would be that there's two simple refrigeration systems that are easily understood and widely known. CO2 is used on the low temp and a low GWP refrigerant on the medium temp. The system operates very efficiently for the CO2 side because it's operating subcritically. The other advantage is that standard HFC components can be used. Very suitable for warmer climates. And then, of course, we already talked a bit about the CO2 emissions in the TWE calculation. So the system looks very good from that perspective. Transitioning to a distributed DX system, this type of system employs all three strategies: lowering the GWP, lowering the charge, and lowering the leak rate. The basic design, essentially is you have a number of smaller racks located closer to the evaporators or to the cases, with the intent to try to minimize the length of run of the refrigerant piping. These would typically have external air-cooled condenser, but could be a multi-compressor condensing unit. And as I mentioned, it would service multiple case lineups and be using a HFC refrigerant. Another variation of that would take the closely coupling the system would be a macro-distributed, where you would have, in this case here, you'd have one condensing unit for a lineup. Now, these would typically be water-cooled condensing units, where the heat rejection would be through a plate heat exchanger. You'd have a closed water loop system, either to a chiller or to a fluid cooler. And the advantage of the system, once again, is to more closely couple the refrigeration equipment with the load or the cases. Then typically systems would have HFC refrigerants. So some of the considerations, typically these systems are going to use a little bit higher GWP refrigerant, such as a 448A. These systems, these types of refrigerant would have a more pronounced refrigerant glide. It's very manageable, but the evaporator or condenser circuiting may change. The other aspect, obviously distributed, is you're distributing refrigeration equipment and by definition the electrical system as well. So that has to be taken into account in store design. And ultimately, there's going to be more compressors and components than a centralized DX. And then for the macro distributed, certainly you have to take care to make sure that you don't have chiller or fluid cooler faults that would affect the entire store or all the systems that are hooked to it. And then in terms of the power distribution or the annual power consumption, very similar to what we've seen previously. Distributed would be the lowest power consumption in this case here compared to booster CO2 and a cascade CO2 system in the simple examples that we've been talking about. So the advantages of distributed system, once again, employing the strategies we talked about, very simple system, very closely coupled systems, and then which results in a very small refrigerant charge. Given the short length of runs, there's lower parasitic losses due to the pressure drop in refrigerant lines. And generally, these systems are very efficient. You can use standard HFC components, and it works well in all environments, all climates. And so looking at the TWE calculation, comparing it to the booster and the cascade, you can see that the effect is more pronounced. In this case, you're considered a 7.5% leak rate for the distributed systems, given that typically the line reductions are going to be at least half, and the system gas charge is going to be half of what you would see in a standard DX, opposed to what we looked at 15% in the previous example. So then, as we take this architecture further from, kind of mini racks to a macro system to microdistributed, once again, we're still leveraging those three strategies, lowering the GWP, the charge, and the leak rate. In this case here, microdistributed means that we have a case with one or more water-cooled condensing units. Each of the units would be charged with R290 with a maximum charge of 150 grams. Heat from each of the units rejected through a plate heat exchanger in a closed water loop system. And the fluid cooler or chiller, fluid cooler can be either dry or adiabatic. So once again, it's a very simple system utilizing cap tube as the expansion device typically. So what are the considerations? Well, R290 is flammable, and so that obviously needs to be taken into account. These systems typically would have ignition-proof components or ATEX rated. Since there's going to be multiple condensing units per case, there's going to be more compressors and components in the store. And the designs really need to take that into account in terms of being able to incorporate the condensing units, make them unobtrusive, but still make them serviceable. So what are the advantages? Well, obviously R290 using natural refrigerant is future-proof from regulation. We've got the refrigerant charge reduced, minimized to probably the lowest level it can be, probably 90% reduced compared to a standard DX system. The other advantage we talked about is that it's a very simplified refrigeration system, DX system, very understandable. All the components are standard HFC type components, obviously rated for propane. The other advantage too is that these types of systems can be made in a factory setting, the manufacturing process, so that the seal integrity is very good. Very low leak rates. The systems are typically single point electric with just one inlet and outlet water connection. So these are very plug and play, very quick to install. So obviously the advantage, of course, is looking at the TWE calculation is very evident. And then the variation of microdistributed would be self-contained with R290, but there's a lot of efforts around designing self-contained equipment to include either HFC or R290. In this case here, I'll be more focused on the R290 systems. Once again, the strategies employed are pretty straightforward: lower GWP and lower charge and lower leak rate. These units these types of cases would all be both open and closed cases, low temp and medium temp. The open cases certainly utilizing R290 may require multiple condensing units. These would be air-cooled condensing units, by the way. So some considerations and advantages are very similar to the, almost identical to the microdistributed. We talked already about using R290 and what those considerations are. The advantages, once again, it's certainly future-proof if you're using R290. The charge is minimized. The same types of advantages that we've seen in the microdistributed. Very simple, very understandable, plug and play, and the advantages of the factory sealed units. So in summary, regulations will continue to drive innovations to address global warming and energy consumption. Now, there are clear strategies that exist to reduce the warming impact for retail stores, and there are many choices available in refrigerant architectures. So what are the factors that influence a choice? Cost is obviously plays a role in any of these kinds of trade-offs. So the first cost, also looking at the total life cycle cost in terms of maintenance and operation. Certainly the expected life of the asset in terms of the investment. The HFC phase down timeline would also play a role. In the system complexity, the availability of technical resources, the availability and cost of refrigerants, energy costs and peak demand costs. I didn't really talk about peak demand costs, but situations exist where there's a high peak demand that has demand charges that also come into play in terms of the system. And then the climate conditions play a role in consideration for any of these types of systems. New versus remodel, and then obviously the speed of installation all come into play. And then the one thing that's pretty clear is that one solution doesn't fit all applications, so all these things must be considered and the trade-offs made. All right, so these are the different references that I used. Thank Emerson for the use of the life cycle climate performance energy tool. And then for those that are interested in more information related to CO2 advanced technology, the multi-ejector paper is very good for that. So with that, thank you. And then if there's any questions, I'd be glad to answer them.
So thank you, Mr. Mike, for the wonderful session. We have a few questions from our audience. The first question is, what are the critical safety aspects to be taken care of in CO2 systems?
Safety in terms of commissioning the equipment, a lot of careful planning in terms of the startup, in terms of training the technicians, in terms of having gauges that are already resident on the rack would be important considerations for safety. The other aspect of safety related to CO2 would be enclosed spaces. So if the system have walk-in coolers or freezers, typically you'll have some sort of leak detection to make sure there's no asphyxiation. Thing for if it's a enclosed machine. These are the main considerations for safety.
Thank you for that answer. Our next question would be, which refrigerant is the best for CO2 cascade systems?
So, ultimately, it's going to be a trade-off between efficiency on the cascade system. So there's different refrigerants available. And I can provide another reference to a paper that talks more about different refrigerants in the cascade system. It might be useful, and I'll add that to this presentation. But the trade-off also will be trying to get the lowest GWP refrigerant on the cascade system. So, and then as regulations change, A2Ls would be available, and then those would have a host of considerations as well, but this would also be a possibility. But looking at the life cycle energy tool that we have on the Emerson site, certainly is a possibility to look at different.
Thank you. Thank you for answering that question. Our next question is, R290 is a highly flammable refrigerant, and in retail stores, they pose more of a flammable hazard. So what is your take on how to mitigate them?
So for R290 systems with grams, a careful consideration in the design of the refrigeration equipment must be considered. So in terms of, if it's a closed case, if it's an open case, those will all be factors. We certainly want to make sure that we're using ignition-proof components. We certainly do not want to have standing R290 sitting in any part of the equipment. So in some situations, you may have a fan running to disperse the R290 if there's a leak. But in general, using ATEX or ignition-proof types of components is a key advantage there. But each of the different types of condensing unit, or excuse me, cases and condensing units need to be looked at very carefully.
Thank you. Our final question for this session is, in India, we have been discussing about CO2 systems for quite some time. However, not many have taken it up. How is it in the other parts of the world? We would like to know your take on that. We would also like to know what is your take on CO2 systems in India?
Well, I think, once again, I think it's a trade-off discussion around the different choices and factors mentioned in the summary. Certainly, it's a viable alternative. One needs to understand, how much time the system is going to be operating in a transcritical mode versus subcritically, and then what's the availability in terms of technical support, in terms of installation, maintenance. Those are the kind of things that really would have to come in any kind of discussion and a trade-off. And then obviously the cost will play a role in terms of the first cost. But yeah, I think that if you look at the rest of the world, Europe is very comfortable with transporting CO2, and a lot of innovation is coming out of Europe relative to enhancements to the standard booster system. So I think that once again, I think those are all around the trade-off discussions and cost. First cost is other opportunities. As I mentioned, there's no answer. It just depends on the application and becoming very comfortable with what are the trade-offs that we're making.
Thank you, Mr. Mike, for the wonderful session and for taking your time out and being here with us today. I also would like to thank all our participants, the exhibitors, the exhibitants who've joined us today, and we trust you had a wonderful first day at REFCOLD. We'll do look forward to having you here with us tomorrow. Thank you very much for joining us.